obviously a relationship here. To me, a little different. Well, the fact that these matrices, and I see that it works.
Right.
And I see how you do it before you start using the matrices.
Right. I'm sorry, Austin.
Does that make sense?
Yeah, I know what you're saying. I would guess that Gauss probably didn't do this. I don't know the history of it quite well. I assume that when this was first started to try to organize these things, someone named it in honor of Gauss because Gauss did so much work in algebra and analysis and all those different things. I assume it was probably more seen later to be able to organize it in this fashion versus in how Gauss probably did it. I don't know that for certain. That's my guess. That's more, more named in honor of Gauss than Gauss actually did. It probably is. That happens a lot, actually. That something's named after somebody that they didn't have anything really to do with it necessarily, or in honor of. I don't remember his first name, but Jordan is the one that did a lot of the stuff with the using row operations and getting them method put in place. So that's probably more where it came from. I guess if somebody else is noticing hey, by the way, you can just play around with coefficients. You don't really need to keep track of the variables as long as you organize it nicely. That was probably the advancement after Gauss. I'll take Dr. Roth. He would know a lot more about it than I would. Because he knows a lot more about history than I do. Yeah. He knows a lot more about it than I do as far as that goes. I don't know the history necessarily behind it. Probably should. You know, Brad probably should know, but I don't know timeline of it off the top of my head. Yeah. Sorry, I can't give you a better answer than that. But like I said, my inclination is that Gauss probably didn't do it this way. But I don't know that for a fact by any stretch. Other questions? I can always count on you for a good question. Other questions at all? All right, so last time we talked about how we could translate a system of equations into an augmented matrix. We should also be able to go back the other direction. In particular, when we get done with our process of solving, we want to be able to interpret what we're getting out of the results so that we can actually write our solutions down. So if you're given an augmented matrix like we have in these next two examples, you should be able to tell me what the system is that corresponds to those augmented matrices. Let's assume that our variables in the first one are x and y, and in the second one there are x, y, and z. How would you rewrite the first one in terms of x and y? Good? Yeah, equals -1. Good. Yep, exactly right. So we're just pulling those coefficients. These are the coefficients. Remember, again, the first column should be the coefficients on whatever you've identified as the first variable, whatever order you're putting on your variables. Like I said, assume your variables here are x and y. So that first column is referring to the coefficients on the x. The second column is referring to the coefficients on the y. And again, the part after the bar is what's on the other side of the equal sign. So you should be able to do the next one as well. What do you get for the next one? Yeah, 2x plus 5y equals -4. Good. X plus 7z equals -2. Good. You don't have to leave the gaps in there. I just like having them in the same column. So leave the gaps in there so they don't look like they're in the same column. Good. We all okay with that part? All right. One of the things that we'll be interested in going forward is the part that just forms the coefficients. So if I look at this part here, that was just the coefficients on your x and y. If I just look at this part here, that was your coefficients on the x, y, and z. If we look at the matrix that's only the coefficients and don't augment it with the constants, we actually refer to that as the coefficient matrix. And like I said, later on, we'll be interested in properties of that coefficient matrix. We'll cross that bridge when we come to it for why we care about that. And for right now, just defining what it is. Okay. Augmented means that we've got these matrices, the matrix that's got the coefficients in it, and the matrix that has the constants in it, and we basically put them together. That's what the augmented part means. So, in systems of equations, and we're going to talk about this in we haven't talked about matrix operations yet, but we'll talk about it in I think it's the next section. But no, sorry, it's not the next section. We have to do another one past that. But we'll have a matrix that's just the coefficients, like this one, and we'll have a matrix that's just the constants, and we'll be able to write that equation, what we refer to as matrix form. We just have to talk about how to do that quite yet. But augmenting it means that we're just taking those two parts and putting them together. That's all the augmented part means. All right. So, pardon me. Our whole goal of this section was to get to the point where we can come up with an algorithmic method for solving a system of equations. We'll actually have two of them. And depending on what you're trying to do with the system, you might want to use one versus another. Okay, so that's why we're going to talk about both of them. One is probably more efficient from a computational standpoint. The other is necessary to do some other operations that we'll be talking about later, or some other interpretations that we'll be talking about later. Okay. So going back up to, did we do one yet? I haven't done one yet. All right. Notice that if we have one of those triangular systems, you've got a matrix that can be written in that triangle. You'll have a matrix that looks kind of special in a triangular form. Let's just say, for example, off to the side here, I had a triangular system that looked like this, and then I'm just making up these numbers as I go. So we talked about when we were doing elimination before, we could put a system in this triangular form. Remember, the triangular form we defined was we had coefficients of 1 on our variables that were leading off in each of those equations, right? And as we moved down, we've gotten rid of a variable, right? Moved from the first to the second equation, we got rid of the x. Moved from the second to the third equation, not only did we get rid of the x, we also got rid of the y. Okay. If we looked at the augmented matrix from the system at this point, notice that we've got zeros down here in this lower left-hand corner, right? And in particular, if I just look at the coefficient matrix in this particular case, notice I've got the only things that are non-zero are the diagonal here and this upper part, right? We would actually refer to this type of matrix as upper triangular. We'll do that definition later. But this is what we refer to as an upper triangular matrix. So that triangular part is talking about that I see this nice triangle of things that are not zero, or may not be zero. The other parts are zero. Yes, Matt. Yep, and that's what we're going to be doing here in a second. Yep, that's exactly right. Yep, the fact that we have ones here is going to be in our form that we have. Okay. So Matt already noticed that we've got ones down the diagonal here, right? Notice that when we've got a 1 here, everywhere we've got a 1 that starts off the row, there's zeros below that 1 down the column, right? And so that's exactly what's going to be important for this form that we're going to talk about. And that form is what we're going to refer to as row echelon form. That's the name of it. Okay. So what are the criteria? Well, we haven't seen the last criteria here that we'll use here in a second. But notice that we've got each row starts off with a 1, right? And that was what we said when we were making these systems into triangular systems. We'll make sure that first coefficient that we saw was a 1, okay? So the only thing that we haven't seen that does also pop up, remember when we got infinitely many solutions or no solution? We might have got a row of zeros here. Okay. So the first thing that we're going to do, I'm going to state this one first, is that all rows of zeros are at the bottom of the matrix, if there are any. Okay. So if you have any rows of your matrix that are entirely made up of zeros, all of those are at the bottom. Okay? The next condition we want is what Matt noticed earlier, those ones down the diagonal idea. The first non-zero entry of any row, if there are any non-zero entries, is a 1. That's the first non-zero entry of any row, unless it's a row of zeros, of course. We refer to these ones as pivots. That's the name we give those. And then what's the other thing that we noticed in this condition? We've got this triangular thing. So anything that's in the same column below a leading 1 must be a 0. Okay? So every entry below a pivot, so in the same column below it, I'll just write in the same column, with making sure that we're emphasizing that. Is a 0. All right, so all rows of zeros get gathered at the bottom. Pivots go the stair-stepping idea from left to right. And then everything below pivots is a 0. Now, it might be the case, we haven't seen one like this yet, we'll see these as we go along. It might be the case that you have something that looks like maybe you have something that looks like this. Okay? So notice here we would have, if we had an augmented matrix that was reduced to this, notice that this would tell us here that we've got 0 equals 0, so we've got infinitely many solutions probably, right? But notice I don't have a pivot right here, do I? So if we're trying to describe the solutions to this system, this one we get a parameter. Because I don't have, notice I can say z equals 2, right? This one would say that x plus 3y minus equals 5. I don't have any information about the y, right? So the y would get the parameter in that case. We talked a little bit about that. We'll do more of those as we go along as well. But this is in row echelon form, the way we have it. So it doesn't have to have ones down that diagonal idea. We could have something shifted over if we lose a pivot somewhere along the line. Like I said, we'll see more of these as we go through more examples. Right now we're just trying to get the definitions down. All right. The last little piece we need is that we also have what's referred to as reduced row echelon form. The last thing we need for reduced row echelon form is that additionally, we need every entry above a pivot is 0. So not only do we get zeros below the pivots, we also get zeros above the pivots. That's what puts it in reduced row echelon form. Row echelon form is good enough for us if we're just solving systems of equations, because we've already talked about putting it doing elimination to where we get that triangular system and then can use back substitution to find the answers. Reduced row echelon form will help us do other things later. Okay. All right. So let's look at some of these examples to determine, are they in row echelon form, are they in reduced row echelon form, or neither? Okay. Now notice, if something's in reduced row echelon form, by default it's also in row echelon form, right? Reduced row echelon form is a little bit stronger. So let's look at this first one. Is this one in row echelon form? Does it meet all of the criteria for row echelon form?
Yeah.
Yeah, it sure does, right? Leading entries in each row is a 1, 0 is below it, right? Is it also in reduced row echelon form? Yeah, so it's in both, right? So this is in both. Oops. Both row echelon form and reduced row echelon form. And we'll use those for the abbreviations REF and RREF. If you, yes. Say that again?
Explain how the first entry
For this example, what's the first entry in this row? If I read from left to right, what's the first thing you see? A 1, yeah. In this one? These are all 1s, right? The first non-zero entry. We ignore the zeros when we're looking at those. Yeah, it's the first non-zero entry that you're interested in. Yeah. We'll use REF and RREF for abbreviations, and you'll notice that if you've got one of the TI-84s under the, and I'll show you how to use that, which I forgot to bring my calculator today. You'll notice that when you do under the matrix commands for those things, those actually are the letters that they use to put them in those forms. Okay. All right. What about the next one? What can you say about the next one? Yeah, it's just row echelon form, right? But not reduced row echelon form. Now notice that if you put it in reduced row echelon form, you do get a little bit of a benefit, added benefit. Notice in this one, we can find the solutions, but we have to use back substitution. This one, you can actually read the solution off, right? Because what is this one? If I use x, y, and z for the variables, what can you literally say about the solutions here? X equals 4, y equals -3, z equals 1, exactly, right? So if it's in reduced row echelon form, I can read the solution off pretty quickly. Agreed?
Yeah.
Okay. What about the next one? Okay, I agree with the row echelon form. What about reduced? Well, what is the extra condition for reduced? You have zeros above. Well, there's nothing above the 1 and the other one, right? So does it violate reduced row echelon form? No. Remember, if to violate it, I have to find a leading 1 where there's not something as 0 above it. I can't do that, right? So this is also in reduced row echelon form. Right? There's only one pivot, agreed?
Yeah.
Do you see anything that's not a 0 above it? No, but I don't see jack squat above it, right? Okay? So this is also in reduced row echelon form. Okay. It's an example of something that's referred to as vacuously true. It's true because it can't be false, right? I can't prove that it's not in reduced row echelon form because there's nothing above it. So it has to be true. So it has to be in reduced row echelon form. If you've taken discrete math, you talk about the empty set being a subset of every set. The reason why the empty set is a subset of everything is because there's nothing in the empty set. For something to be not a subset, I have to find something that's in the first set that's not in the second. Well, I can't find anything in the empty set, so it has to be a subset. I can't contradict it not being a subset, so it has to be a subset. That's vacuously true. If it can't be false, then it has to be true. That's what vacuous unanimously true means. All right. What about the last one? Is that in either reduced row echelon form or row echelon form? No, it's not because of this one right here, correct? In order for this to be in row echelon form, this would have to be a 1, and it's not. Right? However, say I just look at the coefficient matrix instead. What can you say about that? Row echelon definitely, and it's reduced row echelon form as well, right? Here's my leading 1, there's zeros below it, there's my leading 1, my pivot, zeros above and below it, that's okay. This one doesn't have a pivot, so I don't need to worry about it. So this would be, the coefficient matrix is both, right? This one would be neither, but the coefficient matrix is.
Because the 0, 0, 0.
Say that again.
Because 0, 0, 0 doesn't equal.
So the reason why it's not in either is because this is not a 1. If this were a 1, it would be in row echelon form, but not reduced. Yeah. The reason why is that the first non-zero entry is not a 1, so that's why it's not. If this was 0, then it would be both. Yeah, it'd be both. If this were a 0 and this were gone, then it would be both. Yeah. So it's neither because it's not a 1. If it were a 1, it would be reduced row echelon form, but not reduced. It would be row echelon form, but not reduced because those aren't zeros. And then if it were a 0, then it would be both as well. That would tell you there's no solution. Yeah. This could be a step that you've gotten to when trying to solve the system, and this would tell you that you have no solution. Yeah. This would be an example of, hey, I went through and tried to row reduce or tried to put this in row echelon form, and I got this statement, so I know that now I don't have a solution. Yeah. Other questions on that? Yeah. Correct. I agree. Well, you could have, with a short example, you could have something like, maybe your matrix your system equation started with something like, maybe you started with that system, that one up there, here in the corner, and then when you take 2 times that added to that, you would get 0 on this side, and this one would be 0. You get 7. That's how you would get to that point. You started with a system that had no solution, but you didn't see it to start with. And as you're going through to solve it, as you're changing things up, then it cut off to that way. Yeah, you wouldn't start with a system that was like this. But, yeah. All right. So we've already mentioned what these next things are. But we're going to do this in the context of playing around with the augmented matrices versus the systems of equations. Remember, we had 3 allowable operations to put a system into an equivalent one, right? We swapped 2 equations, we multiplied an equation by a non-zero constant, or we did a multiple of an equation, added it to another, and replaced the other equation. Okay? We're going to do, but we also just said that all we really need to do is keep track of what the coefficients are as we go along, right? So we're going to do these with just the coefficients and on the matrices, and we're going to refer to these as elementary row operations. And there are 3. The first one is swap 2 rows. The second one is multiply a row by a non-zero constant.
The last one is multiply a row by a constant. Add it to a second row and replace the second row. And again, just to remind, this leaves the first row unchanged. We did these are just changing what we did for operations for rewriting a system into an equivalent one that help us write out what the solutions are. We're just translating this over to matrices. So far, our first interpretation is just using these augmented matrices to help us solve systems of equations. But we're going to see throughout the course of the semester that there's lots of different things with row operations that we can do that don't necessarily pertain to solving systems, but will allow us to rewrite matrices in reduced row echelon form typically and help us interpret situations. Being purposely vague because we're not there yet. Okay. But there will be doing elementary row operations to matrices that aren't explicitly tied to solving systems, is what I'm trying to say. Okay. That's why we're translating it over to matrices, even though so far all we've done is solve systems. Okay. All right. So the idea behind we're going to use these elementary row operations to help us put our matrices in row echelon form. The process that we use is what's referred to as Gaussian elimination. All right, so we'll write out what the steps are for our Gaussian elimination as we go first. Okay, so what do we want to try to do? Well, remember again that we want to try to get the whole goal of this before was to try to get our system into a triangular form, right? So notice how we did that before. The first thing we did was got a 1 as our coefficient for our x, right? And then we eliminated the x's below it. Then we got a 1 for our coefficient for our y. We eliminated the y's below it. And then we just keep going farther and farther to the right. That's exactly the process we're going to do. We're just going to translate it over to matrices. So the first thing we want to do is get a pivot as leftmost as possible in the first row. What do I mean by that? Well, you might have started off with maybe something that looks like this. I'm just making it up. Notice that I've got a 1 as my first non-zero entry in my first row, but that's not as far to the left as I could get, right? Because this row here has something that is non-zero, right? So the first thing I would want to do in this case is swap those two rows around. So I got a 1 up there as leftmost as possible. That makes sense? What's next? Well, remember when we started doing the systems of equations, we got a 1 for our coefficient, and then what did we do next? We eliminated the x's, right? So the second part is, oops. Why are you not writing? It's being really goofy. That was weird. Oh, why are you being a jerk? Yeah, barely ran out of ink. That's weird. What are you doing? reattach it and see if it figures out that it's supposed to be connected or not. Stop. What are you doing? Apparently, maybe I'm done recording because I don't have. That was weird. It's not even acting like the pen's connected. That's bizarre. Oh, now it's going. Maybe. Well, for a second. Why are you being a jerk? Alright. Can I use my finger? No, because my finger wants to scroll. Alright. Guess we'll do it the old-fashioned way and go on the board.